Hello, my name is Florian Fuhrmann and I welcome you to the presentation of the project EDCSproof. EDCSproof focuses on the control of energy supply systems in industry. To give an example, the energy supply system in a bakery provides the process heat needed for the baking process. In this presentation, we will see why providing process heat for baking bread is a challenging control task, why model predictive control is the method of choice to meet those challenges, and the control concept developed during the project EDCSproof will be presented. Let's have a look on why providing process heat for baking bread is no longer a simple control task. The decarbonization of power production has led to a transformation of energy systems. Power production is more and more depending on the weather and therefore no longer controllable. Therefore, the power demand needs to be controlled. For the industrial bakery, this means that the heat has to be produced in times of energy surplus and not necessarily when the bread is in the oven. This has also caused changes for the power market. Industry companies can now benefit from flexible energy prices and the power control market. For our industrial bakery, this means that by controlling the energy demand accordingly, the energy costs can be reduced significantly. Naturally, reducing the energy cost is just a side goal of a producing industry plant. It is inherent that product quality requirements are fulfilled. Advanced control can accomplish that while simultaneously reducing energy consumption and increasing energy efficiency. Also further goals like CO2 reduction can be considered. These partly conflicting goals and the new power market make the supply of energy for baking bread a complex undertaking. Luckily, digitalization enables control methods which meet those challenges. Let's look at these challenges from the view of a control engineer. The transition of the energy system leads to two new disturbances, the weather and the energy price. The new power market brings new market constraints to the system, for example, a maximum energy consumption at a certain time. The product quality requirements bring new process constraints to the system, and the competing goals change the single set point to multiple objectives. The CO2 production has to be weighed against the wear of a CHP, or the energy efficiency has to be balanced with energy prices. The correct weighing of these different objectives is a complex decision and demands interactions of the operator with the system as a new input. Luckily, digitalization also provides some methods where the plant can benefit from these new challenges. Predictions of the weather and the electricity price allow a predictive and flexible operation of the energy supply system. New industrial computers enable mathematical optimization for real-time control. Therefore, the objectives can be formulated as an objective function, and also the constraints can be brought into the optimization problem. The last method which is needed for a holistic and optimal control of the energy supply system is the model, a mathematical description of the plant. With the model, the trajectory of control variables can be calculated with given plant inputs. Together, these components, the predictions, the objective function, the constraint, and the model, enable the so-called model predictive control. Model predictive control calculates an optimal trajectory for all plant inputs and outputs by solving the optimization problem in each time step. This is the essence of model predictive control. We have seen that model predictive control meets all the challenges of controlling an energy supply system. So why is this method rarely applied in industry? There are some challenges remaining, hindering the implementation of model predictive control. During the project EDCSproof, solutions were developed. The first challenge is the modeling of the energy supply system. It is a very time-intensive and resource-intensive task which has to be repeated for each new plant and at each significant change of the plant. Therefore, a modular implementation method was developed and validated during the project EDCSproof. It allows an effective and purposeful implementation of the MPC. The second challenge is the interaction of the operator with the control system. A human-machine interface was developed which visualizes the key performance indicators for the operator and transforms interactions of the operator with the system into changes of the objective function or constraints the system can handle. The third challenge is the intense computation effort of real-time optimization of the energy supply system. Even though computation performance has increased in the last years, the online optimal control of energy supply systems is still a challenging task. This challenge is intensified by the long prediction horizon which is needed for the optimal control of the energy supply system. Therefore, a two-layer optimization was introduced, where the higher layer considers only the long-term effects, while the lower layer considers the short-term effects. The last challenge, but definitely not least important fact, is the information which is needed for the optimal control of energy supply systems. Often, sensors are missing in industry plants or important states cannot directly be measured. Therefore, an observer was implemented into the control system. Together, all these solutions were called Energy Demand Control System by the project team. Short, EDCS. Let's recap the work that was done so far in the project EDCSproof. The EDCS was developed from the basic principles of model predictive control. It was tested thoroughly in simulation studies, and the performance was validated in laboratory environment. Therefore, EDCSproof is a successful project as it brought the EDCS from Technology Readiness Level 1 to Technology Readiness Level 4. And we are very happy that the journey doesn't stop here. The follow-up project, Industry for Redispatch, already started. This Navy flagship project has a main goal to implement the EDCS in 3 industrial plants and thereby reach Technology Readiness Level 7 by 2025. Thank you for your interest in the project EDCSproof. You can find further information and publications concerning MPC below this video. If you have any questions, don't hesitate to contact me or my colleagues. Thank you for watching this video.